And we also review dry bump temperature. Dry means not wet, bump, this is the bump, temperature of an air is measured by just a normal unmodified thermometer. You just use a thermometer like this, you measure the temperature of the air, and what you read dry bump temperature. For example, now in this room 27 degrees C. Okay, let's go dry bump. You just measure normally. So when people tell that the air temperature is 30, that means the dry bump temperature of the air is 30. Specific heat of water vapor. This is the average specific heat of water vapor, 1.88 kilojoule per kilogram degree Kelvin. It is smaller or higher than the specific heat of liquid water. Smaller, right? What does that mean? Means that to increase 1 kilogram of water vapor to 1 degree C, you need less or more energy than to do that to liquid water? Less. Okay, I will just review you a little bit here so you understand, you remember. So what I draw is the heating or cooling of water together with the phase changes. Now we start from ice. If we do this at normal atmosphere, okay, pressure, atmospheric pressure 1 atmosphere, then we start from ice, and if we do heating, we supply the heat, and then we increase the temperature. At what degree C ice start to melt? 0 degree C, right? At 0 degree C, ice start to melt from solid into liquid. When 100% of ice is already melted into liquid, if you still supply the heat in, you do heating, the temperature of the liquid water will increase, right? And at what temperature the liquid water start to boil? What temperature? 100 degrees C. 100 degrees C, then the liquid water start to boil, and then liquid water is converted into what? Vapor. When all the liquid water become vapor, if you continue to supply in the heat, the temperature of the vapor will increase. Okay, if you supply it in the heat. Now if you do the same, but you do in opposite direction, means you release the heat, you take out the heat, then it will go the same. So like this. If you start from here, okay, you go down, and then in here, these two lines should be overlap. Okay, I will just try to draw it a bit away from each other so you see it, but actually it should be opposite, it should be the same. Okay, and then like that. If you go this direction, then you should what? Take out the heat. Remember, what I draw happens at what pressure? Atmospheric pressure. When you change the surrounding atmosphere, the temperature, the melting point, the boiling point would change. Okay, it's not the same anymore. And then what do we see here? Now the heat you supply, when you supply in the heat, you change the temperature of the water, and that heat is called what kind of heat? Sensible heat. Sensible heat is the heat exchange. Either you supply in, you take it out, and there is according change in temperature. You can feel it, you can sense it. So it's called sensible heat. But there are two periods on this process, here and here. This heat, you see, there is a heat exchange. Either you supply in or you take it out. But there is no change in temperature of water. And that is called what heat? Latent heat. It's a hidden heat that you cannot feel it, because there is no change in temperature. Because during those two periods, there is a phase changes, not the temperature changes. Okay, so here we have melting heat, and here you have like evaporation heat. What is this? How do you call this? If you convert from liquid to vapor, how do you call this name? Evaporation or boiling. If you go backward, how do you call? What is the term? If you go backward, condensation. Okay. And then if you go like this, how do you call it? Freezing. Freezing or crystallization. And you go this way, you call this what process? Melting. Okay, those are the terms. In some drying technology, particularly free drying technology, you can convert directly from even ice to vapor. And how is this process called? Sublimation. If you go directly from vapor back to ice, you call deposition. Right. Now we just review a little bit further how to calculate total energy that you need to supply in to increase the temperature from here, for example, minus 18 degrees C up to 110 degrees C at atmospheric pressure. How to calculate the total energy. Then you need to calculate the total energy each stage, each period, and then you just sum up all. And then how to calculate from, for example, from this point, I may call this point A. Something wrong with the pen, I don't know why it always makes some noise. I'll just change in color. If you need to calculate A to B to C to D, E, and then F. Okay, the energy to increase from A to B will be what? The specific heat of ice multiplied by change in temperature, what? 0 minus 18. Okay, energy would be equal to also the mass of water that you need to increase. If 1 kilogram, then no M here. But if you increase 10 kilogram, for 10 kilogram of water, then you have to multiply by 10. Okay, that's how to calculate. And for this one, how do you calculate? M multiplied by the Cp of what? Of liquid water, right? I think something wrong with my laptop. After the break, I will just restart my laptop. Okay. And then here you have the Cp of liquid water. Okay, Cp of liquid water multiplied by the change in temperature would be 100 minus 0. And the energy here, how you calculate? Also the same, the amount Cp, but not of liquid water, but of what? Vapor. And a temperature would be 110 minus 100. So by just applying simple formula like that, you can already calculate the sensible heat you need. Now, how do you calculate the melting heat here and the evaporation heat here? Here you don't have a formula, you have to use steam table. You have to use the table, and then they will give us the enthalpy for melting, and they will give on the table the enthalpy for the latent heat here, the evaporation. You just multiply by the mass, multiply by the mass. Okay, in some slide we will see, we'll just look at the table later now. Right, so this is the specific heat of vapor. Specific heat of liquid would be 4.18. Specific heat of ice somewhere 2. accurate number we see somewhere else, or you can search somewhere on a book. So what do you see here is at, well, you look here at the 2CP. Liquid water has a higher content of energy, right? The CP is higher, means that you need higher energy to increase temperature, or you obtain higher energy when you reduce the temperature. That is why water is used a lot at the heat medium, to heat food, to heat something else. Enthalpy of water vapor. This is the enthalpy of water vapor in the air. You have, this is normal, we already know, the CP of vapor multiplied by the difference in temperature. This is the dry bulb temperature of the air. This is the reference temperature, but you have to plus by this. And what is this? Why do we have 2501 here? Very high number. This is the evaporation enthalpy for water. Before it become vapor, it should convert from liquid into vapor, and this is the enthalpy for that. Okay, did you bring the saturated steam table? I will just open it and we'll see. Or we go somewhere here. Okay, you go. I think I paid it somewhere below here. This one at 0 degrees C. This is the enthalpy of C, mean condensate, mean before it starts to boil. HV is enthalpy at saturated vapor, means it's already converted completely to vapor right at the point that I will show you later. And then this is enthalpy there, and from here to here will be HL, means the latent heat for evaporation. You use this, you subtract this one, then you will obtain HL. You remember this one, we increase here. So here we have is liquid, here we have 100 vapor. But actually in this table, they indicate here a C. Why they indicate C? C means condensate. Because when you go backward, you obtain 100 condensate. You go to this direction, you obtain 100 vapor. So they put here C. And HC is the enthalpy at this point. HV is the enthalpy at this point. And now you need to calculate the HL, will be the enthalpy for evaporation will be here. You this one, subtract that one, you obtain this. Okay, I will go back. So this is actually the HL, the latent heat for evaporation at 0 degrees C.